is how mobile application app establishes connection to confidential VM. This is a figure about establishing a trusted secure connection. I will explain it step by step. Just like other presentation in this summit, we adopt a security model which does not trust hypervisors. Mobile phone app client should establish secure connection to confidential VMs and should send sensitive information only to trusted confidential VMs. Attestation report is issued by AMD processor, and this report shows the hash of the initial memory state of confidential VM. Its measurement value is one of trusted hashes. The client can understand that the state of initial memory is the same as a trusted one. The next page shows what is folded into measurement. We boot VMs like that using direct kernel boot, where Linux kernel, initially, and kernel options are passed directly to virtualization software like libvirt and kem. In this way, kernel and kernel options are also expanded into the memory when booting, so kernel and kernel options are also folded into the measurement. This means if the measurement matches trusted one, BIOS kernel and kernel options are in the trusted state. Attestation report is signed by the AMD secure processor and can be verified against AMD's certificate chain. Attestation report has a 64-byte field, which the confidential VM can request to embed arbitrarily 64 bytes. Typically, applications running in confidential VM can embed the hash of public key, and by using this public key, client can establish secure connection to the confidential VM which generated attestation report. Like this, in this configuration, mobile phone application can establish secure connection to confidential VM, which is verified to have BIOS, kernel, and kernel options the same as trusted one. Next, I will explain implementation in IaaS layer. To realize our confidential VM in our private cloud, we needed mainly 3 changes for OpenStack cluster. One is SEV-SNP support. We cannot start without it. One is setting kernel options in a situation of confidential VM. And one is VM scheduling so that the measurement changes only when users expect it. The first thing is SEV-SNP support. Current OpenStack supports SEV-ES, but does not support SEV-SNP. We implemented SEV-SNP support in our private cloud. We are also contributing to OpenStack Nova. I'm assigned as a contributor for this feature. Our POC code for defining the spec for the feature is already in upstream Gerrit, and we are preparing a follow-up patch to align with the finalized spec and resolve conflict. Second, I will talk about kernel option. We needed some modification about kernel options from OpenStack to match confidential VM situation. Direct kernel boot itself was supported by OpenStack, but we had 2 gaps to realize our confidential VMs. One is that in OpenStack, VM image has property of kernel options, and there is no option to be modified when booting. In our confidential VM, application-related options should be also included into a kernel option. Therefore, we added an option so that users can specify options when creating VM. Therefore, in our confidential VM, kernel option of VM is combination of the one specified tied to the VM image by IaaS operator and the one added by VM users. There was another gap to realize our confidential VM. Current OpenStack does not work if the kernel option is longer than 255 characters. We modified to work with longer options, and we plan to upstream it. Third, I will talk about VM scheduling. We had to configure OpenStack so that measurement does not change unexpectedly. In SEV-SNP, AMD certificate chain is generated for each CPU generation. And AMD certificate chain corresponding to the server CPU generation is not installed in the client, as the client fails to verify the server. And there was even more specific factor to be fixed. The model of vCPU, or CPU ID more precisely, also affects measurement hash. If vCPU model is set specifically, it is not a problem. But we want to use pass-through CPU model. The model of the vCPU is the same as the host CPU. This means if we set pass-through CPU model, the slightest change of CPU model affects the measurement. To solve this problem and users can expect measurement, we configured so that users can specify CPU model in the flavor selection. In this way, while IaaS operators can deploy new hypervisors at any time, users can control when a new measurement appears at the server side. By the implementation I explained, we had the three things available in our confidential VM. First, we added SEV-SNP support. This is planned to be upstreamed to OpenStack. Second, for direct kernel boot, we improved to match our situation. Both OS image manager in IaaS operator side and VM users can configure kernel parameters. And we extended the maximum length from 255 to much longer, which also plans to be upstreamed. Lastly, VM users can control when the measurement changes, while IaaS operators can deploy new hypervisors at any time. This is by the flavor tied with CPU generation and CPU ID.
Next, I will explain how we keep the service application trusted inside the confidential VM. In the previous section, you saw how attestation can be used to establish trust in a confidential VM and how we implemented SEV-SNP support in OpenStack. In this final section, I'll show how we extend that trust from the confidential VM itself to the service application running inside it. This diagram shows the overall system again. For the rest of this section, we'll focus on the area highlighted in red inside the confidential VM. Our goal is to allow the client application to determine whatever it is safe to communicate with the service and send sensitive information to it. To achieve that, we need to ensure that the service running inside the confidential VM can also be trusted. This leads to questions. What does a trusted service state mean, and how can we achieve it? In our implementation, we define a trusted service state using two conditions. First, the specified service must be launched without modification. Second, the service must remain unmodified after startup. The service consists of two components, the operating system and the application container. Therefore, both components must be launched as intended and remain unchanged while the service is running. If these two conditions are satisfied, a client can make trust decisions based on the actual software running inside the confidential VM. The next question is how we achieve these guarantees. We achieve these two conditions through two mechanisms. The first mechanism ensures launch time integrity. The operating system and application container are specified through kernel command line parameters. Those parameters are included in the attestation measurement, allowing the client to verify what was launched. The second mechanism ensures runtime integrity. We apply operating system configurations that prevent modifications after deployment. Together, these mechanisms also allow us to satisfy both requirements shown on the previous slide. Let's first look at the operating system and application container launch. The operating system and application container are identified by hash passed through kernel parameters. For the operating system, we use a DM verity root hash. For the application container, we use a container image hash. These values are part of the kernel command line and therefore become part of the attestation measurement. Inside the confidential VM, DM verity uses the OS root hash, and our in-house launcher uses the container image hash. Together, these components ensure that intended operating system and application container are launched. Let's first look at the operating system side. The operating system root file system is protected by DM verity and mounted read-only. A writable root file system would allow persistent modification after boot. As a result, the state verified through attestation could diverge from the actual running system. At the same time, services still need writable storage for logs, temporary files, and other runtime state. To solve this, we place a writable overlay FS layer on top of the verified root file system. Runtime writes are redirected to the overlay FS layer, while the DM verity protected root file system remains unchanged. As a result, the service can operate normally while the attested root file system remained unchanged throughout the service operation. The application container is selected using the container image hash provided through kernel parameters. Our in-house launcher reads that hash, retrieves the corresponding images from the registry, and launches it. An important point is that the launcher itself is part of the DM verity protected operating system. Because the launcher is protected by the same trust chain, the container image specified the hash is launched as intended. At this point, we've shown how the operating system and the application container are launched as specified. The remaining question is how we keep them unchanged after startup. Attestation reflects the states of the confidential VM at boot time. If someone could log in afterward and modify the system, the verified state and the actual running state could diverge. To prevent that, we disable interactive access to the operating system. Specifically, SSH login and console login are disabled. Combined with the immutable root file system, this prevents external modification of both the operating system and the application container. As a result, the service remains in the state that was verified at the startup. This satisfied both requirements we introduced earlier. The service is launched as specified, and it remains unmodified after launch. To summarize, SEV-SNP attestation enables secure communication with confidential VMs. We implemented SEV-SNP support in OpenStack and are contributing that work upstream. And finally, we extended attestation-based trust from the confidential VM to the application container. By combining attestation, kernel parameters, DM verity, and our container launcher, a client can verify both the operating system and application running inside the confidential VM. At the same time, cloud users can deploy containers with minimal configuration while still benefiting from confidential VM attestation. Thank you for your attention.